Okay, good day. So we'll be discussing about a continuation about fuel and energy efficiency innovations. Okay, so we'll be go to fuel efficiency. Actually, most of the topics in some of the topics in energy recovery systems will be back in the fuel efficiency because they are connected from each other. Okay, so fuel efficiency is okay. Calm seas or raging storms, the engine never sleeps, and neither do we. We are the marine engineers. Okay, so that's our motto for today. Okay, let's start. So, fuel efficiency in marine propulsion. So, we have here a diagram. Uh, so, from the engine, so mass of fuel is injected into the diesel engine, and then is, uh, power will be, or the efficiency will be um, this one, and this is the efficiency of the engine. So, not 100% of the fuel is converted into 100% of efficiency. So what they do is from the exhaust from the engine, like the exhaust gas. So this will be used to power a gas turbine, for example, or a turbocharger, or an economizer, and then that one, and it will add an efficiency to our total efficiency, combined efficiency. Add efficiency from the turbine. Next, some of this exhaust will be used for steam generation, like the economizer, and then this steam will be used to run a steam turbine, and then another fuel efficiency will be added to our combined efficiency, but not really 100% of what you put in the engine will be used. Some There are still some of the efficiency that will be lost along the way. So, fuel efficiency in marine diesel propulsion is a key factor in reducing carbon emissions, operational costs, and environmental impact. So, with increasing regulations for the IMO and global efforts toward decarbonization, improving fuel efficiency has become a primary focus for ship operators. So, modern technologies and innovations aim to maximize energy output from every unit of fuel while minimizing waste and emissions, helping ships comply with IMO 2023 EEXI. So this is Energy Efficiency Existing Ships Index, improving the technical performance of existing ships. And Energy Efficiency Existing Ship Index, and CII, the Carbon Intensity Indicator Regulation. EEXI and CII regulation. Okay, so let's go with the key innovations in fuel efficiency for marine diesel propulsion. So letter A, we have the electronic fuel injection, EFI, and fuel optimization system. So we've discussed a little bit about this common rail system, right? And then they are using this electronic fuel injection. So this one, the principle replaces conventional mechanical fuel injection with digital control for precise fuel metering, reduces fuel consumption by optimizing engine injection timing, improves combustion efficiency and reducing unburned fuel and emissions, lowers CO2 and NOx emissions to meet IMO Tier 3 requirements, improving efficiency by 5 to 10%. So this is a common rail type of a system in which the the electronic control is the one that is controlling how the fuel metering, how many fuel is injected, the timing of the injection, the rate of injection, if it's um, if the three injectors inject the same or there is a pattern, so whatever. So all controlled electronically. So this is another key innovation in fuel efficiency. Another key innovation in fuel efficiency is for slow steaming and engine derating. So in principle, operating the engine at reduced speeds to decrease fuel consumption. So lower RPM, lower fuel consumption. Benefits: reduces fuel usage by up to 30% in large vessels. Extends engine life by reducing wear and tear. reduces carbon footprint by minimizing fuel burn. So these are the technologies used for slow steaming and engine derating. So let's first we'll go to electro assist turbocharger for slow steaming. So for slow steaming, so of course the engine is running slow, so the exhaust is also slow. So to compensate with that, we have here a motor generator. If you are in a slow steaming mode, you can use this motor to help the turbocharger run. But if you are in full speed ahead, so you can use this motor generator to generate electricity for the ship. Okay, so this is like the hybrid turbocharger, but you can use this as a motor also. Okay, so that is for the electro assist turbocharger for slow steaming. So slow steaming, lower exhaust, so lower turbocharger speed. So to compensate, we have a electro assist turbocharger. Okay. Another one they use for slow steaming is the slide type fuel valves. So this one, so in fuel goes in at the center, and then this pink one will be moved up, pushed by the amount of fuel, and then going into this green one, and then the green one will also move up, and then going through this hole, and then getting out of the nozzle. Okay, so that is a slide type fuel valve for slow steaming. So they changed their injector type for slow steaming to have a better control of the fuel and then more optimization. Also using the turbo cutout for slow steaming. So if you have a low exhaust generation, so you can cut off one of your turbochargers so to maintain the turbocharger efficiency of your turbocharger, the efficiency of your turbocharger. Okay. So benefits for slow steaming upgrades. Apart from running at part load, there are a number of ways to further increase the financial benefit from slow steaming. These measures enable reductions in fuel and lubricating oil as well as an improved engine performance, adding significant further gains to the annual savings achieved by slow steaming itself. So such solutions are turbocharged cutout, slide fuel valves, alpha lubricator upgrades, and engine derating with the option of a new propeller design. So what they do in this engine derating is they will use a much smaller engine, but with the option of new propeller or much efficient propeller design. So lower, derating the engine, smaller engine. So smaller engine means smaller fuel consumption, right? But to maintain the efficiency, they will have to improve the use a new propeller design for this one. Okay, another key innovation in fuel efficiency for marine diesel propulsion is the exhaust gas recirculation and water injection system. So, in principle, recirculates a portion of exhaust gases back in the engine to lower combustion temperatures and reduce NOx formation. So, this exhaust gas recirculation is putting back some of the exhaust, cool it down, and then put it in the intake side to lower the exhaust or the NOx formation during combustion. Okay. So this improves fuel efficiency by optimizing combustion. Also, you can use water injection to lower down the NOx formation. How does this work? So we have a water tank here, a pressure transformer, and a flow fuse. And then water is injected. This is the water needle, and this is the fuel needle. So during the um, injection of fuel, water is also directly injected into the combustion chamber. So if you lower down the exhaust temperature, you lower down the NOx formation. So that's what they do. In this EGR, if you put carbon dioxide into the intake air during combustion, you also lower the exhaust temperature by because of the carbon dioxide. So you also lower down the NOx formation. So that's how they do it. Okay. Another key innovation in fuel efficiency for marine diesel propulsion is using alternative and low carbon fuel. So we have low carbon fuels like LNG, LPG, methanol, ethanol, so many. We have also carbon neutral, no carbon, or very small carbon. So we have biofuels and biomethane, synthetic methane, and SNG. For zero carbon, we have hydrogen, E hydrogen, and ammonia or E ammonia. So in principle, using fuels with lower carbon content or renewable alternatives to improve efficiency and reduce emissions. So types of alternative fuels, liquefied natural gas reduces CO2 emission by 25% compared to HFO. Biofuels produced from renewable sources offering up to 80% CO2 reduction. Methanol and ammonia, future fuels with zero sulfur emissions and potential for carbon neutrality. Another key innovation in fuel efficiency for marine diesel propulsion is hull and propeller optimization, like using this air lubrication system, okay, or hull lubrication, air lubrication system. So improving hydrodynamics to reduce fuel consumption by lowering resistance and enhancing propulsion efficiency. Injects air bubbles under the hull to reduce friction, cutting fuel use by 5 to 10%. Also, energy saving propellers and rudders. So they are using different types of techniques to have energy saving for fuel efficiency. So fuel efficiency and fuel saving propellers and rudders. Advanced blade designs reduce water resistance and improve thrust efficiency, like this one. So they can use this one using surf bulb, super stream duct. There is Mewis duct. So there are so many ways to improve the hull and propeller optimization of ships. Also, hull coatings and cleaning. So hull and propeller optimization. So special coatings minimize biofouling, improving speed and fuel efficiency, and then less friction with the um, sea. Another key innovation in fuel efficiency for marine diesel propulsion is the hybrid and electric assisted propulsion. So you can use diesel generator, you can use fuel cell or ESS system to for your propulsion motor. So uses battery storage and energy recovery to supplement diesel engines. The benefits reduces fuel usage by utilizing stored energy during a low power operation. Enables zero emission operation in port area. So pag nasa puerto, if you are in port, you can close this or shut off this generator, electric diesel generator, and then you can use the fuel cell or electronic system, or you can tap with the power on the shore. Enables zero emission operation in port areas. Extends the lifespan of mechanical components by reducing engine load fluctuations. So you can also use solar panel, batteries. You have mm, what else? You can maybe use wind turbine if okay. So another key innovation fuel efficiency for marine diesel propulsion. So another key innovation fuel efficiency, but this is not for marine diesel. So this is the nuclear marine propulsion for cargo ships. So, advantage of nuclear propulsion. So, clean source of energy. Nuclear power is an extremely clean source of energy. It produces little to no gas pollutants. This makes it a very desirable alternative to diesel engines that produce several hundred tons of pollutants in every voyage. So, nuclear power has the potential to solve the global climate crisis, as studies show that it can reduce CO2 emissions by 98% compared to conventional fossil fuels. It also eliminates SOx, NOx, and particulates matter from the energy generation process. Advantages of nuclear propulsion, so lower weight. So has considerable weight. The shield around the reactor core makes up most of the weight. However, it is lighter than the conventional marine diesel engine setup. Thus, for every kilowatt produced, less energy is spent on propelling the dead weight of the ship. This allows us to increase cargo capacity and improve the operational efficiency of a ship. So this is your molten fuel core. And then water is pumped through it, and then steam is generated, and then this steam will be used to power a steam turbine, and then powering a generator, and then a motor, and then maybe a gearbox to the propeller or whatever what how you use it. Okay. The fuel for a nuclear plant is also stored in the reactor itself. Thus, the fuel storage doesn't require additional space. Another advantage, high design speed. So the use of nuclear propulsion enables us to design for higher operational speeds as the fuel cost increases. only marginally with higher speeds. The ultimate limiting factor in the case of nuclear reactors is the power rating, as it determines the capital expenditure. So this is your reactor. This is put in a reactor compartment to reduce or to prevent radiation leakage. Okay, and then water will go to the secondary circuit to run the main turbine, which the main turbine is clutched to a gear, reduction gear to the propeller. And then another steam will also run a turbo generator. That one. Okay, another best advantage, the most part, the best part of having a nuclear propulsion is fewer refueling stops. So one of the underrated advantages of a nuclear power based system is that the duration between refueling can be considerably longer than traditional engines. This can be useful in large vessels such as VLCCs and ULCCs that rarely visit ports. So, as seen with nuclear submarines, which can go up to 30 years without refueling. Grabe. So, for 30 years without bunkering, okay na yun. Mas less na yung trabaho natin, di ba? Hindi na tayo, we will not be, we will not, we will have our proper sleep because during bunker, usually we don't have proper sleep. Okay. Advantages is feasible operation. So, since it is used in naval ships, in submarines, so syempre, we can also use it in our merchant ships. So just limitations on nuclear propulsion is the security and safety concerns. Usually your reactor is placed at the center. So to prevent from being damaged from collision on front or the back. And then the nuclear energy has been used in military ships and submarines for a long time, but their use in commercial ships exposes civilian life and infrastructure to unprecedented risk. Even though the current technology makes it very unlikely that a meltdown would occur, controls need to be put in place to prevent nuclear accidents due to grounding, impact, collision, machinery damage, fire explosion, and other causes. Another limitation is complicated monitoring. So there's no doubt that nuclear technology is advanced and complicated science. Merchant ships are manned by civilian engineers with no background in nuclear energy. Thus, the operational dynamic of the nuclear propulsion plant is complicated. But through training, so maybe is easier for me. Risk of nuclear leakage. So, while doing away with fossil fuels eliminates the risk of oil spills and pollution, the use of nuclear power presents new types of risk. The risk of nuclear leakage and subsequent damage to persons, property, and the environment could be much worse than oil pollution. Although the risk of a meltdown in the reactor post for commercial shipping is close to zero, controls still need to be built in place to ensure that nuclear leakage incidents do not occur. So, grabe yung protection. We have secondary shielding, we have the containment vessel, we have the secondary shielding, then a collision protection on the side to prevent from collision. So it's a very almost close to zero um, meltdown. So these are their protection, so many protections. And then some other limitation is the social political risk. So nuclear marine propulsion carries the risk of public opposition and other social political risk when wide-scale implementation begins. So public depende sa public. But it's high capital expenditure, of course. You will have to expend high during startup, but for 30 years without refueling, that's so your nuclear has a longer lifespan than your ship, right? Your ship usually 15, 10 years. Some fleet just say sell their ships after 10 years or 20 years. So this is how they work. We have here a reactor, and then water is produced into steam to run a steam turbine, and then the steam turbine will run a generator. It can also be another turbine to your propulsion also with reduction gear. Mhm. So there are three reactor designs after analyzing 93 concepts in the International Atomic Energy Agency SMR handbook. So we have the best used um, reactor designs for commercial or for merchant ships. We have the thorium fueled molten salt reactor, lead cooled fast reactor, and helium gas cooled reactor. So this is a molten salt reactor, thorium fueled molten salt reactor. This is the picture. Simplified example arrangement of nuclear power service vessel. So we have there the core, protected core. We have a nuclear waste handling spaces at the bottom. So steam is used to run a steam turbine. Mhm. Actually, this was already used. Nuclear ships were run at 1950. It's a long time ago. They've been using this on submarines, cruiser, submarine, India, submarine. But it's been used for a long time now. Maybe we can. It's high time we can use it on merchant ships also. We have here the Soviet Union icebreaker, 1959, 1962 merchant ship, NS Savannah, 1969 Germany's cargo ship, and 1970 Japan's Mutsu cargo ship. So it was also used in cargo ships. Yeah, another design, reactor compartment, and then the steam side in here. So this is the chemical uranium. The uranium is neutron. Ooh. Presently, about 200 ships are using nuclear marine propulsion plant technologies. The most popular ship types that use these technologies are icebreakers, submarines, and aircraft carriers. Of course, icebreakers are far from bunkering stations, so it's better to use nuclear, which has 30 years of no bunkering. However, the shift towards sustainability has led to a rising interest in nuclear propulsion for commercial ships. Using it would allow ships to operate more responsibly concerning the environment. The UK in 2021 invited inputs from the industry regarding the use of nuclear power for merchant ships. Nuclear powered ships. Many ships companies are also actively researching and commercialization of molten salt reactors through partnerships with research institutes. We could see the construction of nuclear ships as early as 2030, so 5 years from now. However, like every other energy source, reliable safety measures must be put in place, of course. So here example, a nuclear powered Russian icebreaker ship. This name. It's Nobel show. I can't read Russian. Okay, impact on environmental protection and energy efficiency. So most of the technologies we've mentioned reduces CO2 and NOx emissions, aligning with IMO 2030 and 2050 decarbonization goals, lowers operational costs, ensures compliance with environmental regulations, extends engine life through optimized fuel consumption, and reduce stress on components. So as the shipping industry transitions to a low carbon future, fuel efficiency will be crucial in achieving IMO's net zero emissions by 2050. So future advancements includes full electrification of ships with renewable energy sources, hydrogen and ammonia fuel cells for zero carbon shipping, integration of AI and smart systems for automated fuel optimization. So in conclusion, fuel efficiency is a key factor in reducing the environmental impact of marine diesel propulsion. Innovations such as electronic fuel injection, slow steaming, alternative fuels, air lubrication, and hybrid propulsion contribute to lower carbon emissions and improved operational efficiency. As the industry moves toward IMO 2050 decarbonization, further advancements in fuel efficient technologies will drive sustainable and eco friendly shipping operations. So I just put all the things that I will have to say. Most of the things I have to read is in the side so that the students can also read what I'm saying. Because some students couldn't really catch up with just hear uh, hearing the voice of the instructor. They also want to read it also so that they can um, um, analyze also the information. Okay, so I hope you learned something today, and our next topic will be performance optimization softwares. I hope to see you in our next video. This is the last topic for our LO 3.2 performance optimization software. Okay, so I'll see you on the next video. Goodbye and God bless everyone.